Welcome, everyone. Ieee Linkola, who recently joined octoScope, will be presenting today's tutorial. So Ieee is our Senior Director of Marketing. He spent most of his career in operations and engineering in various product development roles, was a fellow of wireless architecture at Altice USA, and most recently worked for AirTies, a leading Wi-Fi mesh vendor. So he has lots of experience in the Wi-Fi market, and of course he also holds a Master's of Science in Electrical Engineering from the, I forgot to ask him the pronunciation on this, but the Aalto University, Helsinki, Finland. So hopefully I got that right. And with that, I'll turn it over to you, Ieee.
Thank you, Chuck. Yeah, no, that's not too bad. You know, as a first attempt. We'll do some private coaching later on. All right. So what we're going to do today is talk about various testing methodologies that people use in the Wi-Fi industry. As you know, when we start getting a product ready to be launched, we typically take it through a number of different types of tests to make sure that it meets the demands of the market. Typically, this starts in some kind of a lab testing, you know, perhaps performed in a test bed, much like the ones that octoScope sells. Quite often, the product is then taken into some kind of open air environment, perhaps a test house, and then finally. The testing might, or very often involves real end users. You know, some people call this beta tests, friendly user tests, but you know, the type of testing that's performed as part of real people's real lives. So the focus, the most of the presentation is going to focus on these two first. We're going to compare these methodologies through three lenses. First of all, how repeatable and reproducible are the results when performed either in a test bed or in a test house. We're going to look at the speed of the testing, very important aspect. You know, we live under big commercial pressures to get the products out, so the faster we can test, the better it is. And finally, we're going to look at how various kinds of real world phenomena can be replicated in this test environments. And the whole presentation sort of has an eye of, you know, what are some industry recommended practices, you know, how people perform these tests in actuality, and you know, how do we sort of find the best role for each type of method so that we can get good quality products out quickly. We're going to use these two words quite a bit during the presentation, so it's perhaps useful to just get some definitions out of the way: repeatability and reproducibility. We call a test repeatable when in successive executions for a test case, we get the same result. You know, we test, we run some sort of a test script, get a result, then, you know, we immediately afterwards run the test again. And, you know, let's say we do this, you know, 5 or 6 times. If we get more or less the same result, we call that test repeatable. Reproducibility is almost the same with a slight variance. Here, we typically are talking about a similar type of repeatability, but perhaps some change occurs in between the test iterations. They might be taken at a different time. For example, you know, we produced some results last week. You know, we presented them to you know, maybe management or something. You know, some results are called into question. You know, can you reproduce these? Well, we go to the same environment again, repeat the results, and if we get the same result, we call that we were able to reproduce. It might be not in the same test, a test bed. Maybe we're an ISP and we found some issue and we reported the problem to our vendor. Now, if the vendor can use, they may be using the same exact testbed that we have, just a different instance of it, maybe in a different city. And if we can repeat the test there and get the same result, we call that reproducible. All right. Now, a very important aspect to understand about our industry is that repeatability and reproducibility of a test are ultimately function of two things, right? The device under test on the one hand, and the test bed itself. And we put a lot of effort and a lot of energy in this industry to make sure that the test bed itself has as little variance as possible, so that when we do get results, and let's say that they are different than from the ones that we got last month, if we have high confidence in our test bed in not introducing any variance into the results, then we can focus our energy on understanding the difference of the test result, and we can focus it on the device under test itself. If we have a test bed that introduces a lot of variability, then we end up spending resources, oh, maybe it's the test bed, let's look, and so it costs a lot of money to troubleshoot those type of issues. So, great care is put into making sure that the test bed itself is not a factor in any kind of variance that we get out of it. This is in fact so important that IEEE had an entire working group dedicate their time for a long time. The working group TGT worked a few years ago and produced a set of recommendations to follow in various kinds of testing. They looked, in fact, at 6 different kind of environments, and the purpose was to identify best practices, procedures that would ensure repeatability and reproducibility of results. They looked at conducted environments, various kinds of over-the-air environments, as well as different kind of shielded enclosures. We're going to look at 2 of these environments in particular because they have 2 indoor environments that are quite interesting when we look at the difference between testbed testing and test house testing. So the first environment they call non-line of sight. So this is sort of their set of recommendations as to how one should test in a test house. They say that the home, this should be a home. It should be an unoccupied home. Nobody should live there. And it should be built out of wood. There should be no active radios, whether Wi-Fi devices or any kind of other devices that might cause any kind of interference. Nowhere in the test house. They go further on to recommend that there should be no people in this test house when the tests are running. Obviously, you have to, in between test runs, you might have to go there. But when the test is running, there should be no people within 50 meters. They're okay with furniture, doors, any kind of loose items. But they say that you should mark the positions in which those items are. So that you can fix them. Let's say somebody comes to the house, maybe sits in a chair, moves it a little bit. Before the next test run, we should be able to return the chair back to its original place. And of course, the motivation here is to take away any kind of variability out of the results. So, a moved couch might block the line of sight visibility. In a test link, it might. There might be some reflections coming out of, a stainless steel appliance if it's changed, etc. They go on further on to talk about air conditioning. You should fix the temperature. You should fix the moisture of the air to within a certain range, as well as they go in great lengths to describe the usage of turntables. Now, why is this important? Well, our devices might have some directionality in their antenna patterns, right? There might be a null into some direction or something. We had a whole other presentation a couple of weeks ago where Lee talked about antennas. And so anyway, to rule out any scenario where we accidentally direct, let's say, the null to the direction of the link of, let's say, the throughput measurement, they recommend that you use turntables to sort of rule out any kind of effects like that, and then you average those results out. In fact, they talk about two different types of turntable procedures. They have what they call stop and stop motion turntables, where when you run the test, you don't move the turntable, but then in between tests you turn it. And then they have another protocol where the turntables are moving. There's an access point, the turntable under the access point, another one under a station, and they even talk about at which rate these turntables should spin. All right. The other indoor test environment that they talk about is, or define, is what they call the line of sight environment. This is effectively an unoccupied floor of an office building. They call for there being a line of sight, unobstructed link for at least 70 meters. This is a long, we're talking about a big industrial space here. Again, no Wi-Fi devices or any kind of interferers. They also say that you shouldn't have any reflective surfaces or obstructions within the first Fresnel zone of the test link. Again, same recommendations on air conditioning and turntables. So that's IEEE saying, well, here are some best practices that should ensure highly repeatable and reproducible results. Let's look at the state of the art as how this is practiced today by various organizations. We spend actually a few days browsing through, trying to find material where people publicly speak about their test house testing procedures. We found quite a bit of material. These were either from device manufacturers. There was quite a few labs that were marketing their services. Here's, we could do test house testing for you. Here's some of our test houses. And then we found also a couple of, sort of not quite labs, but more like consulting companies that also do this type of testing, testing for hire. In fact, I have myself personally been in this business in the past as a partner of a consulting company. We had a line of business in this space as well, so I have quite a bit of experience in this space. So I suppose so. Here's some pictures from the material that we were able to find. This is all publicly available. I'm not disclosing anything that anybody couldn't find themselves. And I suppose the first observation is that people are indeed using real homes. What's interesting is the recommendation on wood frame buildings is not strictly followed. We see clearly, brick buildings and buildings made out of concrete in this sample, and that's kind of understandable if you think about it, right? If in your local market buildings are mostly made out of brick or concrete, then why would you go and test in a wood frame building? It doesn't really make a lot of sense. It makes sense for the test house to reflect, the sort of the local construction practices. Now, if we look inside the houses, we do see furniture, loose items. That these places look like homes. There's televisions and coffee makers and microwave ovens. We don't see people consistently following the idea of marking things in their places. Some people do that, many people don't. So there seems to be some freedom around that. Further, in a lot of the material, we see people. In fact, people using what clearly are Wi-Fi devices. So that's interesting. Remember, IEEE said there should be people within 50 meters and certainly no Wi-Fi radios. So this is sort of a little bit curious, but if you think about it for a second, it's really quite understandable, right? There's a lot of activity in making sure that the tests run. Even if you have automated your system very well, there's going to be glitches in the system, and just the smooth operation of the test house basically requires a test engineer or two to be present. And it's understandable that they use computers. The system needs to be controlled. Tests need to be run, and computers usually the user interface that you do that. In fact, they probably also have, internal clients, management asking, well, how's the testing going? Are there any big bugs that I should be aware of? So they probably do internal reporting as the testing is in progress. So clearly sort of varying protocols are followed. Now, I'm not saying everybody's doing it this way. Some people are quite, strictly following the IEEE recommendations. So, but the organizations that are a little bit more loose, they in fact say that this type of variability is in fact kind of welcome, right? If you think about our devices are going to be used in a home, and there's going to be variance in the home. So to have some variance in your test environment is in fact not such a bad thing. Perhaps individual test executions as you do them one after another, perhaps they're not perfectly repeatable, but as long as you take the same test a few times, maybe you repeat it 6 times or a dozen times, if you can achieve, if the average is repeatable, then you still have control over your test procedure, and you can sort of trust the results, right? So these unknown and uncontrolled parameters, to a degree, seem to be, in fact, welcomed. Now, turntables, not everybody is using turntables. That seems to be kind of rare. Some people are. Here on the right, we have a picture from courtesy of .11 Labs, one Wi-Fi testing company that sells their services. They are using turntables here in the picture. In fact, that's a sort of a modified octoScope turntable that they've taken out in the field and modified it for the purposes of .11t testing. There are robots. People are using robots as well. Here on the left, we have a very cool looking robot moving devices around in the test house. This seems to be on wheels and probably has some sort of an optical navigation system. We hear stories about rail-based systems where people move test devices in the houses using monorails and the such. Some of this testing, even involving robotics, is stop motion testing only. Some other organizations also do motion testing while or testing while the devices are moving. So, all right. So there was sort of one set of recommendations coming from IEEE. How you get repeatable and reproducible results. Folks are following it to a degree. Some, your mileage varies. So let's look at what that might mean in practice. Like, how much variance are we really talking about? So I'm going to show you 2 data sets. One was performed by myself in a past life, where I was doing these type of test house projects a little bit. There's nothing special about this test case. I mean, I have dozens of these samples, but just to show a data set. This was done a couple of years ago with an old ASUS model. I'm just going to show one test point where I had a MacBook Air and did some iPerf measurements and executed the test a few times. This was performed in a duplex apartment in a very densely built city, so you're going to see some variability in the results. I performed a download test at some distance. I did it on 5 gigahertz as well as on 2.4 gigahertz, and as you can see, the 5 gigahertz data set is fairly consistent, right? You get 20 executions of the test, same test case, give pretty much the same result. The 2.4 gigahertz band in this environment was very, very congested. I mean, we're talking congestion of airtime, easily 40%, if not more, depending on time. And so as a result, you see a lot of variance in the results as well. The mean looks like about 100 megabits per second, but you see, variance over and above and below. We have another data set here that was now done in a controlled test bed. This particular case, we sort of tried to roughly replicate the previous scenario, but just do it in a test bed. So we used attenuators to sort of reach a similar type of speeds. And again, we execute the test here 20 times. In this particular data set, we run everything with nothing changing during the minute. So we have the attenuators set up at certain levels. We run the test for a minute, take an average speed throughout the minute, and then redo that 20 times. And as you can see, you get an incredibly stable result. I mean, there's some variance, but it's like fractions of a percent. It's 0.02% to be exact. Now, here's a second data set also done in a test bed. This is slightly different test procedure. This is, what people in the industry call a rate versus range test. So essentially, there is, in this test setup, there is an access point and a station, and a single throughput measurement is going on throughout the test. But what we do is we attenuate the air link using 5 dB steps along that throughput test. And we do that, I think the step was 10 seconds in this particular case. And what's happening is as the link budget changes during the test, the MAC layers of the 2 radios adapt to that change. The dB change is almost instantaneous, talking about milliseconds here, but the MAC layer takes a little bit of time to adapt to that. And then the throughput test procedure itself adapts to the MAC layer adaptation. So there's a little bit of changing variables here in the result. And what we are reporting here are 5 runs of rate versus range test. And we're looking at the individual 5 dB steps. Even when this change happens during the test, and even when each individual step is only 10 seconds, we still get very little variation, about 0.2% in this case. So this is kind of expected, right? Repeatability and reproducibility are in fact designed into this type of test bed itself. In the Octobox case, we're using highly isolated construction. This eliminates any kind of variability from the outside. We're using RF absorbing foam inside the chamber to create a semi-anechoic environment. It basically reduces the multi-path effects to almost nothing. Maybe you get a couple of reflections, but the signal is so attenuated at that point that there's very little multi-path happening inside the environment. We have some connections to the outside world, electricity, for example, but it's through filtered ports. So no interference is injected through those ports. And of course, the entire test procedure is done using software controllable test instruments, software and scripts. So no human needs to touch the device or the test bed itself when these tests are performed. And in fact, we also have a turntable, in case we want to do any kind of orientation style testing. So because the repeatability is built into the environment results, it's not a surprise that in fact you do get repeatable results. All right, so that was sort of the repeatability lens. Let's look at some aspects related to speed of testing. In order to sort of set this up, let's imagine a scenario where we're perhaps interested in the performance of an access point. Perhaps we have a new product that we're interested in launching, and we want to characterize the performance of that product. So typically, this type of effort involves a couple of different dimensions of real-world use case. And we run into this problem that I call the n by n problem. So what do I mean by that? Well, a performance of an access point, really is a function of, we might be interested in looking at how it performs in 2.4 gigahertz, how it performs in 5. We might be interested in the uplink performance, downlink performance of different kinds of stations. We might be interested in a high-end, let's say, a laptop that has a multi-MIMO capability, maybe a medium device, maybe like a smartphone, and maybe a legacy device. Maybe we're interested in a joint performance of all of these devices mixed in. Certainly, we're interested in distance and sort of different locations in a home. How does it perform when the station is close by, a little bit further away, kind of in the far end corner. And to rule out any orientation issues, we might be interested in a few turntable positions. So with this example alone, if you test all of the permutations of all of these variables, you end up with 288 test scenarios. Nothing unheard of. People do this type of characterization every day of the week. So that's a lot of work. And let's say we do it, for the purposes of building an argument here. Let's just say we do it manually in a test house where we have some background interference. So we're interested in repeating each of those 288 test cases. And let's say we use a super simple test protocol where we spend a minute executing the test. We spend a minute checking the results, saving results, making sure that everything's going smoothly. Repeat that cycle 6 times, and then spend another 2 minutes of reconfiguration and what have you before we go to one of those other 288 test scenarios. With this type of test protocol performed manually, the data collection in our example alone takes almost 2 weeks. 67.5 hours of data collection time, assuming you don't have to repeat anything, right? That's taking breaks and everything. That's practically 2 weeks of data collection. Now, at the end of that 2 weeks, all you have is a bunch of test results files. Close to 2,000, in fact, and you'd have another 2,000 PCAP files. Let's say you took Wi-Fi interface traces as well. So it turns out when you do this manually, and I've done this a lot, it's extremely easy to make mistakes during this test. You forget to execute one of the 288 scenarios, maybe you do execute it, but you had the devices misconfigured. It wasn't quite the scenario that you were intending to test. Maybe you did test it, but you lost the files, or maybe you didn't lose the files, but you named them wrongly. So later on, when somebody, is looking at the entire campaign, it's sort of a little bit unclear what result files correspond to what test case. Now, typically, and very often in that type of protocol, the person doing the post-processing is not the same person doing the data collection. So it turns out that if you do have remaining mistakes in your data set, it's very difficult to spot them. I mean, it takes hours of looking at the data and making sure that everything looks good, tests that are taken further away from the access point, that they are in fact showing lower speeds and things like that. And it takes a lot of energy to find those mistakes, but in a test campaign like this, it's almost guaranteed that you'll have some mistakes. And so you'll end up sending the data collection teams out there in the field, for another day or two, just to make sure that we have full files. And post-processing this into a report takes a lot of energy. Now, compare that doing the same type of characterization in a testbed, right? We have software controllable instruments. They can, we have instruments that can look like access points, can look like different kinds of stations. In this test, they can look like a high-end Wi-Fi 6 device, and 5 seconds later, we can configure them to look like an old legacy device, that supports maybe ABGN on 2.4 gigahertz only. Because we know that the tests are highly repeatable, we don't have to repeat the test. We only test a test once, and in fact, we can even shorten the time window from a minute to just a few seconds because we have such high confidence in the result. So the bottom line is that the same campaign that took 2 weeks to collect the time, and maybe another week into post-processing, this collapses into a project of maybe 1 or 2 hours. And we have high confidence in the result because there was no humans involved in making mistakes. And in fact, we have even packet captures for everything if there's some interesting post-analysis that needs to occur, right? So, of course, what I was talking about there was really the benefits of automation. So, of course, people can and in fact have automated test house testing procedures so that they get many of the same benefits. Now, you still run into issues. You have to repeat perhaps the test cases a few times, unless you automate these things, you're going to run into a lot of problems. Now, finally, let's look at the ability of a methodology to replicate real-world phenomena in the world. This is important, right? Testing in a testing phase of a product, perhaps we're launching a new product that may be deployed in the hundreds of thousands or millions in the field. We want to make sure and expose the product early on to as many scenarios as possible. Why? Because we want to see if the device under test exhibits any kind of weird behavior or bugs in certain scenarios, right? So if we catch them early in the testing, then fixing the bugs is going to be a lot quicker, a lot cheaper, and we're going to have more happy customers in the end that maybe may make repeat purchases in the future. So with that in mind, let's have a real look at these test houses that we looked at before. So we said that the test houses reflect local market conditions, and to a degree that makes sense. But that causes an issue. Let's say you're an ISP, let's say in the USA, but your vendor may be established in another country. They may not have access to a similar test house as what you are using here. And this might cause an issue of reproducibility between your organization and the organization that's supporting you. Hence, I think IEEE recommended the usage of wood houses. Wood houses are the sort of the cheapest form of construction. So probably there's more wood houses out there in the world than many others. But if we look at a little bit more closely these houses, there's clear selection bias here going on, right? These are big houses. They're not. These are places where the wealthy people would buy. That causes. It's sort of understandable, right? Because in a testing scenario, we want to test cases that happen a little bit further away from the access point. So it's of course useful to have a long distance possibility in the testing, but it causes the selection bias problem. And as we all know, big houses come with big lots, right? So we're not really going to, if our argument surrounding the test house testing is that we want to test our products in sort of typical environments, then these are not typical environments at all in where our products is really going to be used. There's very little apartments, for example, that people use, but people live a lot in apartments, especially in cities. The other problem is that most testing organizations really only have one or two test houses. They don't really necessarily have the business to sustain more. Now, some testing organizations have many houses. We know of companies that run even a dozen. But the challenge that comes with these type of things is due to logistical issues, any single test campaign is usually only executed in one test home only, or perhaps the work is split between two. But it's very difficult to split a single test campaign, in between 12 test houses. That requires a whole other level of automation and coordination. That's difficult to do. Not impossible, but people haven't made those investments yet. So, anyways, but maybe just raise the abstraction level a little bit and see, well, we're interested in testing real world phenomena, but what might those real world phenomena be? Let's take again the example that, let's say we have an access point here, and we want to expose that access point in the testing phase to as many real world phenomena as we can. So what are some of those real world phenomena? Well, number one, the access point is likely going to be interacting with lots and lots of different kind of stations. There's just a vast variety. High-end devices, low-end devices, legacy, new ones. There's different output power levels, beamforming, MIMO. The Wi-Fi industry is now over 20 years old. So, you're going to find a lot of different kind of devices. There's the question of distance from the access point. So, we want to look at the performance close by and further away. There is the phenomenon of mobility, right? Especially very relevant with mesh products. There's handovers in between the mesh nodes. There's various kinds of multipath environments out there. With Wi-Fi 6 and with OFDMA, the first sort of efficiency-oriented Wi-Fi standard, test cases involving lots of different kind of stations transmitting simultaneously becomes important, because the OFDMA radio interface performance is really stress tested in an environment where there's a lot of different stations sort of competing for the air bandwidth. Of course, there's different kind of interference scenarios, co-channel, adjacent channel, maybe high priority interferers, certainly a lot of interferers that are not Wi-Fi at all. And then the introduction of mesh, which is now happening in quite big numbers out there, introduces a whole other dimension of problems, right? How many mesh nodes do I have? 1, 2, 3, more? What kind of backhaul am I using? Wireless, wired? Maybe, do I have a dual band, or do I have a dedicated radio for my backhaul? Various kind of test scenarios that would be good to test. And of course, backhaul now has its own interference considerations. So in this table, I'm sort of trying to summarize sort of our views of the testing methodology's ability to replicate these phenomena. So the 12 dimensions of real worldness, if you will, from the previous slide are now horizontal rows in this table. And we have two columns, one representing the octoScope testbed, and the other one representing a test house. And we're using color code here. Green meaning that we believe that kind of real world phenomenon is easily replicated in that test environment. Devices and automation exists. Red means there's some fundamental issues with the testing methodology and the level of the real world phenomenon. And then yellow, let's talk about the yellow in a second. So focus on the red, right? These are all the interference scenarios with the test house. So if you have a test house that's in a densely built environment, you're going to have interference coming from that environment. And while you, of course, can inject new interference into your test scenario, it's gonna sum with the background interference. And so you don't really have interference under control, right? So hence, we can't really say that you can sort of fully capture real world phenomena like that. Now, let's say you have your test houses in a more of a rural setting with no houses nearby, and let's say you follow these IEEE recommendations to the letter, where you have no people, no radios, then you could certainly do this. But you run into this other problem that we mark here by yellow. So essentially what we're saying is a lot of different kind of testing is possible in a test house, but it very quickly becomes kind of complicated to execute. Not going to go through all of it, but let me give you a couple of examples. Let's look at the top two rows there, right? So the question of the device type, right? We see in the the test house service providers that market their services make claims like, well, in our test houses we have 100 different kind of stations, so you're able to test your system against any and every kind of device out there. Well, that's impressive, right? 100 different kind of devices to test, but just think about automating that, right? To just get a traffic generator client onto all of those devices to make sure that they are powered and on and configure it with the right settings, is a complexity all on its own. Now, let's take the question of distance from the access point. So now we're moving 100 devices from location to location. Let's say we're interested in the performance in 6 or 10 different locations. Well, that's a lot of movement. We need those robots or somehow otherwise do it. And let's just say we're even interested in mobility. So anyway, it becomes very complicated very quickly. And you're going to have to ask yourself, well, how am I going to run this automation? Now, our point of view and things that our customers have done is they have we sell quite a bit of our equipment to these organizations where you can take, for example, in this particular case, the customer has bought a turntable from us, and they've put it on a cart that can then be used in a test home. We have our server here also installed on the same cart, and now you can bring a fully software controllable turntable that's well designed for into your test environment. In this particular picture, we have a customer that's taken one of our PAL test instruments. This is the device that can act either as an access point or various kinds of stations, and sort of we've made a field version of it with a bunch of antennas. So as you think about automating your test house test procedures, it makes a lot of sense to reuse investments that the companies like us have already made, because we have the instruments, they're all software controllable. We have servers running softwares, test scripts, so you don't have to sort of reinvent the wheel and can use the investments that we have made. So to wrap things up, we think that the testbed testing is a very good method for sort of your baseline repetitive tests. You do get highly reproducible results that you can trust. It is by far the fastest method out of the three, and it can reproduce almost any real world phenomena that you can pretty much think of. I mean, having been participating in this type of projects a lot, let's say you start getting some signal from the marketplace that that maybe there's some new strange behavior that customers call you about. A lot more time typically is spent in understanding the problem, reading trouble tickets, talking to the CSR person that talked to the customer, maybe perhaps talking to the customer itself. A lot more time is spent in this area. Once you understand the phenomenon and know actually what happens in there, it's usually not a problem to replicate that test in a test bed, so that from now on you're going to test that before launch. Now, on the other end, friendly user testing. We didn't talk about this a lot, but it's an absolute must usually in these type of projects. It's the best methodology to find these new surprising test scenarios. A couple of years ago, I was involved in a project where we started getting reports that a certain type of Wi-Fi controllable electrical plug was causing issues in the marketplace. No way we would ever learn about this product, but it turned out that I think it was Costco had started selling a lot of these, and suddenly the market was flooded with these devices that they all had weird Wi-Fi behavior. How are you going to find this unless you do friendly user testing? The issue with this is that you get sort of qualitative, not quantitative results. They're very fuzzy reports, and so you have to spend a lot of time understanding what the issues are. It is the slowest and the most expensive method of the three, but you can't really omit it. Now, test house testing, we believe, is a sort of a good intermediate step to take as you move from testbed testing to friendly user testing. It's really great for prototyping these test scenarios that you get from friendly users and from the marketplace, to sort of try to characterize the problem and understand what's going on, so that with the eye on being able to then replicate the test in a testbed. It's also a useful step as a sort of a sanity check as you go from testbed testing to the market. Maybe there are people in your organization that aren't as familiar with what's going on in the testbed. It's sort of useful to gain wider confidence in the product to test it in an open environment as well. You can make the argument that, look, we got this result in the testbed, we got the same exact result in a test house, so therefore you can trust this data and this report. There are issues in testing in a test house unless you automate things to a high degree. This will be a big investment, but if you use instruments that you're familiar with from a testbed, you can reduce this investment cost quite radically. So that concludes the presentation. I didn't hear any questions or.
So we do have one question that just came up from Alec. He's asking, do companies use test offices to test how their device under test operates in an office? Office environment is different than a home's.
They do. I mean, yeah, folks like it depends on what kind of market you test for. So I'm more familiar with the consumer electronics side of the market. So that test is almost exclusively done in homes. But of course, there's vendors like Cisco and the target more the enterprise market. So they're more interested in testing, in an office-like environment. So I would suspect that they have this IEEE line of sight type of environment replicated in some tests.
I personally tested in an office, and it was an empty office that we rented, and there were just cubes, but no people working there. There was no line of sight, but there were longer distances, and you're right, it's a very different environment. We got more range in that environment. But yeah. I remember struggling if we were testing late into the evening, and then we would come back in the morning, we could not get the same measurements.
Yeah,
that's so hard.
Yeah, these are congested. Office environments, as we know, are highly congested during the daytime. So, yeah, it's difficult. Also, I mean, there's also lower output power, so that's another sort of thing that factors into that sort of testing. But yep, I'd say when I was searching for the material regarding this test house service providers, certainly most of them market to the consumer side of the electronics industry. Not sure why. All right. Well, if there's no further questions, thank you for attending. We keep doing this as long as you show up. We're thinking the next topic will be mesh networks. It's a kind of a hot topic in our industry right now. Lots of ISPs are launching mesh products. They're not quite yet super widely deployed. Maybe a percentage or two penetration into the base, but we see this as a sort of a watershed moment where probably that's going to change. So certainly something that we keep thinking about here at octoScope as to what are some problems in that space and how might one build good test procedures to capture the essential phenomena in mesh networks.
I'm not seeing other questions. I guess that being said, I guess we again thank everybody, and just remember all these seminars are recorded and will be available as soon as we process this one. So again, thanks for attending. We'll see you next time.